Experiment number 4, the open channel flow experiment, is going to be looking at kind of two parts. The first part I want to talk about are the study of weirs. Now, weirs are obstructions which are placed in these open channels, which are kind of like an aqueduct, or what it means is it's flow, like we're going to be studying like flow in a U channel. So the top surface is open to the atmosphere. So the fluid is not contained by walls on all sides. So different than what we saw, let's say, in pipe flow, where when we study pipe flow, we're really implying that the fluid is completely filling that pipe. So it's touching the pipes, the walls of the pipe at all points along the circumference. All right, so here, when we put an obstruction, the interesting thing is we can use that obstruction to measure flow rate, all right? But in order to do that, we'd have to know what the discharge coefficient of that object was. So here we can see that there's what we call a sharp crested weir, which is like a vertical wall placed in, let's say, a river, or again, this U channel, and it has a sharp edge on it. And so the flow is going left to right, and so what's going to happen is the flow is going to build up on one side, and it's going to spill over that wall. Now, interestingly, we can see the equation for the flow rate. So the flow rate Q is 2/3 times the square root of 2 times G times L, which is the width of the channel, times this discharge coefficient times that height H raised to the 2/3, where that height H is simply the height of the water level above the height of the weir, right? So this distance, as long as that distance is known, you'll be able to get the flow rate Q. Again, assuming you know the discharge coefficient. So what we're going to be doing in the lab is we're going to use the apparatus to know what the flow rate is. We're going to measure the height here, H, and with that information, we're then going to be able to rearrange this equation, solve for what the discharge coefficient is in our experiment, and we're going to compare that to empirical formulas like we see below here, right? Now, depending on the shape of the weir or its geometry, you're going to get different values of the discharge coefficient. So in addition to looking at a sharp crested weir, we're going to look at something called a broad crested weir. The important thing here to note when you're building your experiment is that there is a rounded edge at the leading edge of the object, and it's a sharp edge at the back. So make sure you install it properly. But again here, knowing this height H, all right, is going to be important in understanding what the flow rate is and ultimately what its discharge coefficient is. Here's the empirical formula for the discharge coefficient of the broad crested weir, and we're going to again compare that to the experimental data. Lastly, we're going to be looking at a V-notch weir. All right, now imagine the flow is coming into or out of the page, and it's a V-notch because it has this little cutout shaped like a V, where this angle theta, in our case this is going to be 90 degrees, is going to help us determine what the flow rate is based on this equation here. Again, knowing what the height H is, where the height H in this case is the height between the water level and the vertex here of this notch, right? Now, interestingly, a V-notch weir has a constant empirical formula where the discharge coefficient is always 0.58. So we're going to, again, compare what we get to this accepted value of 0.58. All right, so that's kind of the first part of the experiment. The second part of the experiment is going to be looking at a different phenomenon in these open channels, which is known as the hydraulic jump. Now, similar to compressible flow, where you might find a shock wave, what happens in these open channels is if you have a really, really fast jet of water, okay, and some obstruction downstream, the flow is going to have to change its speed. And so it does that somewhat abruptly, or it can do that somewhat abruptly, depending on what the Freud number is. So the Freud number is analogous to the Mach number in compressible flows, but the Freud number, as you see here, is a ratio of the inertial force to the gravitational force. So what happens is the flow upstream, we're going to lower a little gate up here, which is going to force the velocity, or excuse me, is going to force the flow through a small area, giving us a high velocity jet, okay, like this. And then we're going to have a tailgate back here. We're going to be able to raise or lower it, and that's going to cause an obstruction. Well, what's going to happen is the flow is going to have to adjust to that tailgate and slow down. And so it does that abruptly where the flow has one thin or small height and then all of a sudden adjusts up to this larger height here where we again get a lower velocity, and here we'd have a much higher velocity. Now there's some loss associated with this jump, and we're going to quantify that with pedostatic probes upstream and downstream of that hydraulic jump. Okay,